Here, we will introduce ourselves to the concept of electric circuits and Ohm's law, which you can view as the most indispensable fundamental law, or we can say the most basic law or the simplest law when we are dealing with circuits. And it intricately connects the fundamental ideas of voltage, which we will develop a more insightful and intuitive understanding of in a moment, and electric current, which is conventionally denoted by the capital letter I. I guess it is to avoid the confusion if they used a capital C with the Coulomb. And what connects these two is the notion of resistance. Resistance that is denoted with the capital letter R. Let me write that as well here. And just to cut to the chase, the relationship between these three is a pretty simple mathematical one. It is that voltage is equal to current times resistance, forming the foundational equation. I will write the equation down here. Or, in another perspective, by dividing both sides of the equation by resistance, we derive that current is quantitatively equivalent to voltage divided by resistance, reinforcing the relationship of the equation as a fundamental principle in circuit analysis. But intuitively, what exactly is voltage? What is current? And what precisely is resistance? And what are the units for them so that we can make sense of this? To get a clearer intuition for what these things are and how they relate, let's build a simple metaphor using the flow of water, which isn't a perfect metaphor, but it definitely helps me at least understand the relationship between voltage, current, and the resistance. Let's say I have a pipe filled with water, closed at the bottom, with water also present above it. The entire pipe is full of water. So, the water right over here is naturally going to have some potential energy due to its position and pressure. And this potential energy, as we will see, is analogous to voltage in an electric circuit. Voltage is the measure of the electric potential energy per unit charge. Now, it is not quite a straight up potential energy. It is actually the potential energy per unit charge. So let me quickly write that down. Potential energy per unit charge. This shows the energy per charge carries. You could think of it as joules, which is potential energy or units of energy per coulomb. That is our unit charge. And the unit for voltage in general is volts. It helps quantify the electric potential difference. Now, let's imagine about what would happen if we now just open the bottom of this pipe. So we open this up. What's going to happen? Well, the water will immediately just drop straight down. That potential energy is going to be instantaneously converted to kinetic energy. And you could look at a certain part of the pipe right over here, and you could say, well, how much water is flowing per unit time? And that exact amount of water flowing through the pipe at that point in a specific amount of time is analogous to current. Current is the amount of charge, so we could say charge per unit time, with Q representing charge and T representing time. So I said previously Q is charge and T stands for time. Hope that is clear to you. And intuitively, you could say it's the measure of how much electric charge is continuously flowing past a specific point in a circuit over time. I am short on space, but I need to write it down for the better understanding here. Continuing with the statement, a point in circuit in a, let's say, a unit of time. So when we say unit of time, we can consider any unit which represents time. We could think of it as a second, and so you could also think about it as coulombs per second, charge per unit time. And the idea of resistance is something that could just partially keep that charge from flowing at an arbitrarily high rate. And if we want to go back to our water metaphor, what we could actually do is we could introduce something that would impede the water, and that could be a narrowing of the pipe. And that gradual narrowing of the pipe here would be directly analogous to resistance. So in this situation, once again, I have my vertical water pipe open, and the potential energy, analogous to voltage, converts to kinetic energy, creating a flow of water through the pipe. But now, at every point in this pipe, the amount of water that is flowing past at a given moment of time is going to be significantly lower because you have literally this bottleneck right over here. So, this narrowing is directly analogous to electrical resistance. How much charge flow impeded? In other words, how much the flow of charge is impeded or restricted in a circuit. I'm noting that down too here alongside. And the unit here is the ohm, which is named after Georg Ohm, which is denoted with the Greek letter omega. And the sign looks something like this here. So now that we have defined these things and we have our metaphor, let's actually look at an electric circuit. So first, let me construct a battery. So this is my battery, and the convention is that my negative terminal is represented by the shorter line here. So I can say that's the negative terminal. The longer line represents the positive terminal. Associated with that battery, I could have some voltage. And just to make this tangible, let's say the voltage is equal to 16 volts across this battery. Let's write down that too, across the both terminals. One way to fundamentally conceptualize it is the potential energy per unit charge. Let's say we have electrons here at the negative terminal. The potential energy per coulomb here is 16 volts. These electrons, if they have a clear path, would naturally go to the positive terminal, and so we can provide that clear path. So let me draw it like this. At first, I will block the electrons from having a path to flow. I have an open circuit here, but I will create a path for the electrons. As long as the circuit remains open like this, it's analogous to a closed pipe. Electrons have no way to reach the positive terminal. So this is the positive terminal of the circuit. But if we were to instantaneously close the circuit right over here, then all of a sudden the electrons could begin to flow through the circuit in an analogous way to the way which that the water would flow down this pipe. Now here, when you see a schematic diagram like this and when you just see these lines, those usually denotes to something that has no resistance, but that's very theoretical. In practice, even a very simple wire that's a good conductor would have some resistance. And the way that we conventionally denote the resistance is with a jagged line. And so let me draw resistance right here this way. So that is how we denote it in a circuit diagram. And let's assume that the resistance here is precisely 8 ohms. My question to you is, given the voltage and resistance, what will be the resulting current in this circuit? What is the rate at which charge will continuously flow past a point in this circuit? Pause this video and try to figure out the answers. To answer that question, you just have to go to Ohm's law. We want to solve for current. We know the voltage, we know the resistance. The current in this particular example is going to be our given voltage, which is 16 volts, divided by our total resistance, which is 8 ohms, following the fundamental Ohm's law. This is going to be 16 divided by 8, which ultimately is equal to 2. And the units for our current, which is charge per unit time, meaning coulombs per second, you could say it as 2 coulombs per second, or you could say it in terms of amperes as well. And we can denote amperes here with a capital A. We talked about these electrons flowing, and you are going to have exactly 2 coulombs worth of electrons flowing per second past any point on this circuit. And it's true at any point, same reason that we saw over here. Even though it's wider at the top and narrower below, the bottleneck ensures that the same amount of water flows through both sections of the pipe per second, maintaining a consistent flow rate. And that's why for this circuit, for this very simple circuit, the current that you would measure at that point, and this point would all be the same. But there's a quirk. Pause this video and think about what do you think would be the direction for the current. If you understand electrons and their movement, you'd note that they flow in this direction. So, for this electric current, I would represent it flowing in that direction accordingly. Well, it turns out that the convention we use is the opposite of that. And that's really a historical quirk. When Benjamin Franklin first studied circuits, he did not know about electrons or their flow. They would be discovered roughly 50 years later. He just knew that what he was labeling as charge, and he arbitrarily labeled positive and negative, he just knew they were opposites. He knew something like charge was flowing. In his studies of electricity, he denoted current as going from the positive to the negative terminal, so the arrow as well goes from up to downside. And so we still use that convention today, even though that is the opposite of the direction of the flow of electrons. As we will see later, current is not always carried by electrons. Other charged particles can also contribute. Here, the current will be a steady 2 amperes.